Hi students, it's Dr. Marks, and we're in part 2 of our hypothesis testing. Now remember, we're still looking at differences in means. We'll do some other types of hypothesis testing later when we get to regression analysis. So we took a little look at confidence intervals and how it connected to hypothesis testing in part 1. We understand one-tailed and two-tailed tests. Now we're actually going to do some hypothesis testing. Remember, we can use the t-distribution to test our hypotheses, but it's also important to remember that our t-distribution converges to the normal distribution for large N, right? And large N are considered to be 30 and above. We like this t-distribution or normal distribution because it has properties that we understand. We've used them already, guys, right? We employed them for constructing our confidence intervals. So before we move on to hypothesis testing, let's just regroup and take a quick look by reviewing our distributions first. So here's our normal distribution. And remember that normal distribution is bell-shaped and it has these properties related to standard deviations, right? We see that if we look plus and minus 1 standard deviation from the mean, we have 68% of our observations. If we look 2 standard deviations from the mean, right, plus and minus, we have 95% of our observations, and 99.7% of our observations will fall plus or minus 3 standard deviations from the mean. Remember that we've been using these upper and lower bounds in our distribution, right? So you see that 90% of our observations fall between positive and negative 1.65, 95% between positive and negative 1.96, and 99% between negative and positive 2.58. And we used those to construct our confidence intervals. So this is something that should be familiar to you already. Remember, we're trying to evaluate if there is enough evidence in order to claim that there's a statistical result, right? And when we say we want to claim a statistical result, we're simply saying we want to rule out that it's due to chance. We're trying to say, look, this result is not due to chance. So to be a significant result, then we have to have enough evidence. And that evidence needs to clear a bar. So I'm going to offer you here, guys, a bit of a goofy analogy, kind of like that fishing analogy that we used with our confidence intervals. But we're going to think about a hurdler. When we do a hypothesis test, for those of you for which this is new, we're going to think about a hurdler. And think about a hurdler. What's he doing? He's jumping. He's trying to clear a bar. So our hurdler is our statistical result. We have some statistic. We're not sure if it's due to chance. And that thing that he's jumping over in red, I'm having a little senior moment here, and I cannot remember what that's called. Oh, duh, a hurdle. All right. A hurdle, he's trying to jump over the hurdle, right? That's the required threshold of evidence. So we're trying to say, look, is the evidence strong enough that we can clear the bar, that we can clear the hurdle? Now, our statistical result comes from our data, right? We've taken samples, we have these means, we want to know if they're different, but this required threshold, right, our hurdle, that comes from the t-distribution, all right? And so you're going to hear me talking about really 2 things that we're going to compare. We're going to compare a t-statistic, again, that comes from our data, our statistical package is going to calculate it for us, and the hurdle is our t-critical, or you might hear me call it the critical t. So one defines the bar that we have to clear to have enough evidence to claim we have really a strong result that's not due to chance, and it's the t-statistic that's trying to clear this hurdle. So really, keep this very simple. Keep this hurdler image in mind, and it's going to make this a lot easier. So let's talk about this threshold, this bar that we're trying to clear, right? That hurdle in my analogy. Where does the threshold actually come from? Remember, we're using our t-distribution in order to determine where that threshold or bar is. that we need to clear. So the t-distribution is going to tell us this threshold or bar. So we have to work with this distribution. And this distribution can be represented in table form. And we're going to use a table version in just a few minutes. And we're going to learn how to read this table. Our threshold that we're trying to find, this thing that we need to clear, is going to be impacted by our degrees of freedom. Now, we've introduced that idea of degrees of freedom before. And our desired level of significance. Just how certain do we want to be? How much possible error are we willing to allow? So remember, we've got to set up our null hypothesis, H naught, right? And our alternative hypothesis, HA. All right. So hopefully this will come together, but it's going to be a little abstract at first. Don't stress. I promise. Just hang with me and I will get you there. So let's look at kind of what a t-test is really doing. And we're going to start by looking at the two-tailed test. Well, why do we call it two-tailed? Well, what do you see? You see this rejection region in both ends of the distribution. That's why we call it two-tailed. So let's start under the assumption that our null hypothesis is true. Now, you've heard me say that before in the previous lecture. Let's start under the assumption that the null hypothesis is true. That's always our starting point. Now, what would it mean for our null hypothesis to be true? Well, if we were thinking about our example with the smokers and the non-smokers, for example, we'd be saying there's no difference in the mean age at death. Smokers had the same mean age at death as did non-smokers. So within this critical values, we fail to reject this hypothesis. So there's some range in this distribution where we're going to fail to reject H naught. We're not going to be able to say that they're not different. But if we're outside of the critical values, and you see the critical values there on our distribution, then we can reject. So take a look at this distribution for a second if this is new to you. We're basically dividing our values into a region where we can't reject the null hypothesis. That's in the middle. And then you see that red sections on each tail. Well, that's the region where we can reject the null hypothesis. So our distribution is basically going to tell us what these critical values are. So these critical values are key. That's really our bar or our threshold. That's that hurdle that we have to clear to be able to say this is a statistically significant difference in mean age at death between smokers and non-smokers, if we're sticking with our previous example. Now, if we're doing a one-tailed test, and remember, think back, what's the difference? A one-tailed test is a directional test. So you think either mean 1 is greater than mean 2, or maybe you think mean 2 is greater than mean 1. Either way, you see that the distribution now only has the reject region only in one of the tails. So that's why we call it one-tailed. So one-tailed versus two-tailed. Remember, with a one-tailed test, we have a directional hypothesis. So remember, I'm saying mean 1 minus mean 2 is either positive or it's negative, right? When I take a difference in means, it's either going to be one's bigger than the other, and depending on which one's bigger, it's either positive or negative. So we've already talked about how to set up a one-tailed alternate hypothesis. So hopefully that means something to you. So all I'm doing here is comparing them side by side so you can see. On the left, I have my two-tailed tests, and you see the reject region in the two tails because I don't have a hypothesis about is it positive, is it negative. I'm just saying, hey, the difference in means is either 0 or it's not 0, right? So it could be positive, it could be negative. If you look on the right, we've got our one-tailed test. Of course, I'm only showing you one of the graphs. I could have given you the reject region in the other tail. So I'm just basically trying to remind you, why do we call it one-tailed and two-tailed test? It's where our rejection region is going to be. Is it in two tails or is it in just one of the tails? Now, let's connect this to this idea of confidence. Remember, we said we need to be, whatever degree confident. We've talked about 95% confident, 99% confident. Well, that connects to this graph as well. So if I want to be, let's say, 95% confident, so if I'm looking at the 95% confidence level, then I have an alpha of 0.05, right? It's the balance. Alpha is always kind of the balance between my confidence level and 100. So if I want to be 95% confident, then my alpha is really 5%, but we write it in the decimal form. So half of my alpha is going to be in the left tail and half of my alpha is going to be in the right tail if I'm looking at a two-tailed test. But if instead we're looking at a one-tailed test, now let's look at the right. If I want to be 95% confident, and again, that means my alpha is 0.05, right? Kind of representing 5%, that remaining 5%. Then that's all going to be in one tail. And again, it could be in the right tail or the left tail. I'm just showing you one of the two pictures. So look at the note at the bottom. I'm reminding you that this is why one-tailed versus two-tailed matters. There's going to be a different criteria for rejecting the null hypothesis. Remember, look at these two and compare. Look at the white regions. Those white regions are where we're going to fail to reject the null hypothesis, that there's just not enough evidence to support that we can reject. So they're not the same, right? That means I have to decide, is it one-tailed or two-tailed? Because I'm going to have a different critical value. In other words, I'm going to have a different bar to clear. I'll illustrate that for you in a few minutes. But let's put some numbers in place just to make sure we understand this. So notice all I'm doing here is showing you that if I'm 95% confidence, if that's my level that I'm interested in, giving me an alpha of 0.05 on the left, that 0.05 is split between the two tails, so I have an alpha of 0.025 in each tail. But on the right, when I have a 95% level of confidence, and now again, my alpha is equal to 0.05, all of that's going to be just in one tail. So significance level is relevant, right? We just saw that. It's going to determine how large the reject region is. And of course, if it changes the reject region, then it's going to change the fail to reject region. If we want to be more confident, well, think about it. If I want to be more confident, then I'm going to have a smaller rejection region. Smaller rejection region means a bigger what? Fail to reject region. And that makes sense, right? If I want to be confident, then I run the risk of having a greater chance that I fail to reject the null hypothesis. And why is that? It's because we're requiring more precision when we say we want a higher level of confidence. So let's compare, and these are not beautiful comparisons, guys. I tried to find the same graph so they would look alike, and I could not do it. On the left, let's actually start with the right. On the right, we're with our 95% level of confidence. So we already understand this. So just looking at the right, we have 95% of our areas in that region fail to reject the null hypothesis. Only 5% of the region is in the rejection region. In other words, my evidence better be pretty strong. I'm only allowing myself a small set of possibilities where I'm going to say we can reject the null hypothesis. Now look on the left where I want to be 99% confident. If I want to be 99% confident, then look at my rejection region, and this is not a beautiful graph, but look at my rejection region. It has shrunk. If you want to be more confident, think about what's happening. You want to be more confident, so you are taking the chance that it's more likely that you're going to fail to reject the null hypothesis. You have a smaller number of possibilities in terms of options where you're going to reject the null hypothesis. So which is it going to be harder to do? Have 95% confidence or 99% confidence? Which is going to be harder? Well, it's going to be harder at 99%, right? That's a higher bar. It's a more rigorous standard. I'm only accepting a little bit of error, and my region for reject, the null hypothesis, right, where that arrow is, that rejection region, is small. As we said, we need to use our t-table here, and that's where our threshold comes from. Our threshold, the thing that we have to clear with our statistics, comes from the t-table. It gives us the critical t value, or t critical value. I'm going to say it both ways. The t critical, or the critical t, and this is important, it's the cutoff point between rejecting the null hypothesis and failing to reject the null hypothesis. It's that cutoff point. If you're below it, you didn't clear the bar. If you're above it, you clear the bar. So guys, this critical t is our hurdle. If I'm below it, I fail. If I'm above it, then I'm successful. So think of it that way. Now, eventually, we're going to compare this critical t to something from our statistical output, right? That's our hurdler. Eventually, we're going to compare this. So back to our analogy, which I know is really silly, but I know some of you are saying, okay, I like this. This is a good way to frame this for me. For those of you who have had statistics, I know you already understand this. But again, on the bottom, my T critical is the bar that has to be cleared by your statistical result. In other words, you have to have enough evidence to clear this hurdle. The hurdler, that's your statistical result. That's trying to clear the bar so that he can be a strong result, a significant result. All right, so let's move on to look at a t-table and finding the critical t. Now, I know some of you are saying, Dr. Marks, why are you not just dealing with p-values? Oh, we will. Don't worry. But that's kind of a shortcut. In my mind, it's a little bit like cheating. You've got to be able to do both to really show you understand. All right, so we have to learn how to read a t-table. And to be able to do that, we need degrees of freedom. Now, anytime we're doing a hypothesis test, there's going to be an equation for degrees of freedom. But remember, we are only comparing sample means with one sample for each treatment, basically. And so our equation is going to be this. Degrees of freedom is going to be N1, number of observations in sample 1, minus 1, okay, plus N2, which is the number of observations in sample 2, minus 1. So we're basically just saying, hey, how big is sample 1? Subtract off 1. How big is sample 2? Subtract off 1. Add them together. We also have to know if we're having a one-tailed or two-tailed test, right? And that's just going to have to come from your own logic, right? You're going to have to decide, do I have a directional hypothesis or not? What would make the most sense? And then finally, we need our desired level of confidence. So there are three things that we need, right? We just listed three. We need our degrees of freedom. We need to know if it's a one-tailed or two-tailed test. And we need to know our desired level of confidence. And we're probably going to be looking at 95 or 99%. All right. Once I have those three things, reading a t-table is easy. So this is a t-distribution. I just grabbed this from the internet. Now look at the picture at the top. This one tells you it's just kind of reporting it under the assumption of what kind of test? One-tailed or two-tailed? One-tailed, right? One-tailed. So suppose that sample 1 has an N of 13 and sample 2 has an N of 13, which means I can calculate my degrees of freedom, right? 13 minus 1 plus 13 minus 1 is 24. Now let's assume we want to be 95% confident, so we're going to be at the 95% confidence level. And again, we know what that tells us about alpha, right? Alpha is going to be 0.05. So from here, all we need next is to know One-tailed or two-tailed test? Well, let's keep it easy since this is reporting one-tailed, and let's just assume that we have a one-tailed hypothesis, all right? So based on all of those things, can you figure out where we need to be looking in the table? Well, we need to be looking in this column right here that I just circled because that is our 5% alpha, right? Our alpha equals 0.05. And I see that right there. Can you figure out our critical T when we have degrees of freedom equal 24? Remember, degrees of freedom are in the first column. So, do we agree? 1.71. So we have a critical T under these conditions of 1.71. Now, some tables will put a one-tailed and two-tailed test on the same table. It's easy to read, but you just have to pay attention here. So look across the top. Do you see it says in parentheses one-tailed or two-tailed? And this is, again, just to make it simple. You don't have to manipulate any numbers like in the previous table. So see if you can find 0.05, an alpha of 0.05 for a one-tailed test. All right, everyone looking at it? So alpha equal 0.05 for one-tailed test. Again, let's stick with our 24 degrees of freedom. Everyone agree we get 1.711? 1.711? And we could do the same thing. What if it's alpha equals 0.05? So we're sticking with 95% confidence, but a two-tailed test this time. All right, so now find where it says 0.05 two-tailed. Does everyone get 2.064? So, do we get the same numbers, guys? No, we did not. So that's kind of interesting. We had the same degrees of freedom. We had the same level of confidence, but a one-tailed test and a two-tailed test had a different T critical, which meant the hurdle is different, right? The bar that had to be cleared is different for the one-tailed versus two-tailed test. We'll come back to talk about why that is in just a minute. If I want 99% significance, now I'm looking at alpha equals 0.01. So let's say we have a two-tailed hypothesis test. Let's stick with our degrees of freedom of 24. So can you figure out where we need to be on this table? So see if you can figure out degrees of freedom 24, two-tailed, alpha is 0.01. So you should be looking in this column right here where it says 0.01, that's our alpha, and in parentheses two-tailed. So we're looking right there, and do you agree? We're going to get a T critical of 2.797, which on a later slide I'm going to round to 2.8, so don't let that alarm you. All right, we know how to read this table, right? Now, really quickly, I've got outlined our critical T under the assumption of a two-tailed test. What if it's a one-tailed test? Can you find that really quickly? So for a one-tailed test, do you see that it's a critical T of 2.492 right there? So once again, we've just shown for the same degrees of freedom and the same confidence level, we get a slightly different critical T depending on if it's a one-tailed test or two-tailed test. All right, we have collected a number of T criticals, right? We did it for 95% confidence. We did it for 99% confidence. We did it for a two-tailed test and a one-tailed test. We've basically done 4 different combinations. Well, let's see what we can observe from this. So we have 4 different numbers, right? All right, so we can make some comparisons, right? We see first that a higher level of confidence has a higher bar, right? Look at 95% confident and look at 99% confident. Which one has the higher hurdle? 99% confident. Well, that makes sense, right? Because we're saying, look, if you want to be more certain, which means you want to have less chance of an error, you better have a more rigorous test. You're going to have to clear a more rigorous test. You're going to have to clear a higher hurdle. 2, we see that our two-tailed test has a higher bar than the one-tailed test, right? For the same degrees of freedom and the same level of confidence, right? Compare 99%, 2.8 if it's a two-tailed test, 2.49 if it's a one-tailed test. So what's that about? Well, remember, with a one-tailed test, you also have to get the sign right to claim significance, right? All of that significance, that alpha level, is in only one of the tails. It's not divided between the two tails. So if you think mean 1 is greater than mean 2, then that's what you need to have to claim significance, right? Because again, with our one-tailed test, we have a directional hypothesis, which I know you understand at this point. Now, we finally get to talk about p-values, which those of you that do some statistics are very used to using. You probably aren't using a t-table all that much, but it's important that you understand both. So our significance level is going to be related to our p-value. And I'm going to help you understand that with some examples. But first, let's understand that a p-value is simply the probability that an observed difference is just by chance. So a p-value is the probability that an observed difference, like my mean in smokers versus my mean in non-smokers, is simply due to chance. And that p-value is going to be calculated by your statistical package. So it's based on your data and it's part of your output. So we're going to get p-values when we actually run the tests on the computer, and I'm going to show you some sample examples. This means if I want to be 95% confident, which remember means I have an alpha of 0.05, that means I'm saying I only want a 5% chance that the observed difference is simply due to chance. I'm willing to only gamble 5%, right? I want to be 95% confidence. I only want to limit my risk to only 5%, that I get it wrong, right? Well, this means then, from your statistical package, that your p-value must be no greater than 5% or 0.05. Because again, your p-value is calculating the probability that your result is simply due to chance. And you've already said, look, I'm only willing to accept a 5% chance that my result's due to chance. So when the computer spits out your p-value, it better not be any higher than 5%, because then you're saying, oh my gosh, the chance is telling me that the chance is just too big. So I can't claim a significant result. So to conclude a significant result, remember, what do we mean by that? We're going to reject our null hypothesis, right? That mean 1 is equal to mean 2, that the mean for smokers is equal to the mean for non-smokers. And that means the statistical package has to compute, if we're 95% confident, if that's our level, it has to compute a p-value that's no larger than 0.05. And if you want to be 99% confident, be at the 99% confidence level, then your statistical package based on your data has to compute a p-value no larger than 0.01. So these p-values kind of help you determine what your results are. In that sense, looking at your p-values is kind of a shortcut. And that's why my students hate it when I make them learn how to use a t-table. They just want to memorize the stuff for the p-values, but then I'll ask them, what's a p-value? And they're like, I don't know. Okay. So our p-values are a shortcut. It gives us a way to quickly eyeball if our null hypothesis can be rejected or not. So a lower p-value, remember, means that there's less likely that it's due to chance. That means low p-value is good. It's less likely that my result is due to chance, that the computer spit out all my analysis and it's saying, look, we don't think there's a very big likelihood, a big probability that this result's simply due to chance. But a higher p-value, on the other hand, then it's more likely that your result is due to chance. So what does that tell us then? We want low p-values, right? We don't want high p-values. So if I generate a statistic on the computer and my output gives me a p-value of 0.27, think about what that means. That means there's a 27% probability that my results simply because of chance. Well, that's not good. So then we know the result's not significant. There's just not enough evidence, right? We're going to fail to reject the null hypothesis. There's just not enough evidence to reject. But if I run my statistical results and I get a p of 0.001, then I'm saying inside, woohoo, that's a beautiful result because that's going to be highly significant. There's a, what is that, 0.1% chance that my statistical results are due to chance. So there's a lot of evidence against the null hypothesis, right? Meaning we can reject the null hypothesis. That's why my students love p-values, because they can just go right to them. They don't have to really think about what the test they are conducting is really doing. They're just like, ooh, p equals 0.27, bad. P equal 0.001, ooh, that's pretty. We like that. That's a strong result. So to conduct our hypothesis test, as I said, we can read the p-values from our statistical output, but here's something you need to remember. Depending on the package, they may, and it's more likely probably, are assuming a two-tailed test. In other words, you're not telling the computer most of the time two-tailed or one-tailed test. Depending on what package, it's just going to assume a two-tailed test, and then it's your responsibility to transform the numbers if you really wanted a one-tailed test. So that means your results aren't quite right for a one-tailed test. If you want to convert them to a one-tailed test, you have to divide the p-value in half. All right? Or, again, we can use a t-table to do this, and I'm going to be super mean, and I'm going to require that you can do both. Understand how to use a t-table so that you can compare critical t to your t statistic from your output and understand p-values. But we'll practice. In my opinion, this is how you truly understand what's going on. All right. So at this point, we understand kind of the components of what we're doing. But now what we have to do is figure out, how do we know if we clear the bar, right? Back to our hurdler. Our statistical results are hurdler, and he's trying to clear the bar. He wants to be a strong result. But we have this hurdle that has to be cleared, that T critical, that threshold. We have to have enough evidence to be able to clear this bar. Now, our T statistic is what is going to help us determine if we've cleared the bar. So our statistical package is going to calculate a T statistic. It's a number. It's going to be part of your output, right? So it's from our data. And that T statistic is basically helping us measure the amount of evidence against the null hypothesis, right? Remember, we want to reject that null hypothesis, so we have this alternate hypothesis in mind. So again, the T statistic is going to help us determine if we've cleared the threshold. So our T statistic is that hurdler trying to jump over our threshold. So that means we need to take the T statistic and compare to the T critical. And we're going to do that in a minute. Now, our T statistic has an equation, and you're going to see it's a function of means, the number of observations in our samples, and our estimate of our variance. So I'm going to show it to you just so you can see, but I'm not going to expect you to do this calculation. Why would we? The computer will do it for us. But our T statistic is that equation right there. And you see it's a function of my two means, A and B, so smokers and non-smokers. It's a function of S, our sample sizes, and N, NA and NB are sample sizes, right? Number of smokers, number of non-smokers, and our estimate of the variance, right? So let's do some examples. Are we ready? If this is a little fuzzy still, do not stress. I'm going to get you there, because really now it's about reading output and using our t-table and our p-values. So let's look at this example where we're comparing some sample before and after some experiment. And it doesn't matter what it is. Just say that we had some treatment in mind, we collected a sample before, and we collected a sample after, and we don't really have any hypothesis about if there's going to be any real difference. Maybe before might be different than after. We don't know if before is greater than after or before is less than after, but I have a mean for each sample. All right, so let's go ahead, just for simplicity, to assume a two-tailed test, right? And again, a two-tailed test means it's not a directional hypothesis. So let's remind ourselves, what would a two-tailed test look like? Our null hypothesis would be that the means are equal. Now, look at our computer output on the left, and you see two means, 0.003 and 0.998. Wow, those seem pretty different, right? But our alternate hypothesis, that's the thing that we're kind of trying to support, right? We generally frame this as we want to reject the null. So my alternate hypothesis is that the means are not equal. And eyeballing that, they don't look very equal. So I'm thinking I'm going to get a strong result here, but I can't be sure till I do my hypothesis test. So let's just be clear, for those of you who like visualizations. We've taken a before sample, and it's got 15 observations, and the output told me that. And we have an after sample, after whatever this treatment was, and we also have 15 observations. I calculate a mean for before and a mean for after, and all we're trying to do is determine, is there enough evidence to claim that these means are different? Is there enough evidence against the null hypothesis? So that's where we're going with this. All right. As we said, we have 15 observations in each sample. How do I see that? Well, go look back to the left, and you see there's a column with n, and it says 15 and 15. So I know that that is my number of observations. That means I can calculate my degrees of freedom, right? So we take sample 1 minus 1 and sample 2 minus 1 and add them together. So does everyone agree? That gives me 15 minus 1 plus 15 minus 1 gives me 28. All right. Now, our statistical output also gives us our t-statistic. Do you see it right there? I've outlined it for us in red, negative 2.45. But here's the thing. Our t-table only has positive numbers. Well, all we have to do is take the absolute value here. All right. So again, some of you are probably saying, okay, negative t, yeah, all right. It would be better if that was a positive number, but just go with me here. T-statistic, 2.45. That's what we're going to work with, and that's what we're going to compare to our t-critical. All right? So remember what we do. We take our t-statistic and we see if it clears the bar from our t-critical. So we need to go get our t-critical. So back to our good friend, the t-table. And we see that I'm going to assume 95% confidence, and that's pretty standard. We've got degrees of freedom of 28. We're assuming a two-tailed test. So does everyone agree I'm in the right place on my t-table? And I have a critical t of 2.048. All right. Everybody with me? 2.048. So we have a t-statistic, the hurdler, of 2.45 and a critical t of 2.05, which is the hurdle. Did we clear the hurdle, folks? So I'm asking, when I ask that question, do we reject or do we fail to reject H naught, our null hypothesis? Well, looks to me like our hurdler cleared the hurdle. So we would say that we reject the null hypothesis. Remember, the null hypothesis said the means were equal. Well, look at those means again. There's really no way we were going to end up failing to reject the null hypothesis. Those are huge difference in means, right? So I probably already knew my answer before I even did my hypothesis test because those were such drastic differences in means, but I still have to go through the exercise. I found my T critical from my table. I see that my T statistic is greater than the T critical, so I'm going to reject the null hypothesis that the means were equal. So that means there is evidence that we have a statistically significant difference in means, which is not surprising given what those means are to begin with. All right. We can also look at our p-value. So p-values, again, is our shortcut. Remember, we're doing a two-tailed test, which is fine because remember, statistical output is generally assuming two-tailed. We have a p-value of 0.028, which means that there's only a 2.8% chance of making an error. And what error would that be? That we get this wrong, that we reject our null hypothesis when it's actually true. So what this means is if there's only a 2.8% chance of making an error, then we're almost 97% confident. But what was my level of confidence that I wanted? I wanted 95% confidence. So guys, have we cleared the bar? Does our p-value help us here? I wanted to be 95% confident. I have a result that is 97, just about 97% confident. So yeah, I can say we can reject the null hypothesis. My p-value tells me that. And it's a little bit easier to look at the p-value, right, than to go look up the critical T. But looking up the critical T is useful. It's helpful to know how this all works. So we've now gotten the result that we fail to reject. That we reject. My bad. We reject the null hypothesis. We did it the long way using the t-table, and we did it the shortcut way with the p-value. Now, what if we want to be 99% confident in our result? So we can go back and do it the long way, right? Compare the T critical for 99%. So let's go grab our T critical. All right, so if we want to be 99% confidence, again, we have degrees of freedom of 28. We are assuming a two-tailed test. Well, two-tailed test, alpha is 0.01, right? Remember, alpha is 0.01 here. Do you agree that our critical T is 2.763? So now let's go back. Our T critical is 2.76, but our T statistic is 2.45. Now, remember, which one is the hurdle? The hurdle is the critical T, right? So this might be in the opposite order that we had before, but you need to understand this so you know which is which. The T critical, 2.76, that's a hurdle we have to clear. Our T statistic is the hurdler, 2.45. Did the hurdler clear the hurdle? No, it did not, right? It did not. So in this case, if we want to be 99% confident, we would have to fail to reject H naught. We can't reject H naught, but we did it for 95%. We just can't do it for 99%. Everybody with me here? Does that make sense? Now, again, we have a p-value of 0.028, which says we have a 2.8% chance of rejecting the null hypothesis when it's actually true. In other words, that's saying we have a 2.8% chance of making an error in our conclusion. So guys, can I be 99% confident? No, because 99% confident means I'm only accepting a 1% chance of making an error, but I have a 2.8% chance of making an error. So can I be 99% confident? No, But do we agree we can be 95% confident? So this is a strong result, but it's not our strongest result, right? 99% would be stronger. But please let me help you understand that if you had a bunch of results that were significant at the 95% level, that is strong evidence. That is a statistically significant result. 99% would be better. That would be like a really, really strong result. So I publish papers all the time using 95% confidence, and sometimes I'm able to show results are confident at the 99% level. But if I can only show 95% confidence, that's still a pretty strong result. People aren't going to go, ugh, Dr. Marks, this paper stinks. You're only 95% confident. This is still a really solid result, okay? Let's look at another example where we're talking about differences in mean salary. So this study is looking at mean professor salary, but it's doing it by rank. And for professors, there are 3 different ranks. We are either an assistant professor, an associate professor, or a full professor. You would come in right out of graduate school as an assistant professor. After getting tenure and promoted, you'd become an associate professor. And eventually, if you continue to publish and you're good, you'll become a full professor. So I'm a full professor, which tells you that means I've been here for a while, but hopefully may not be the case. Hopefully full professors are paid more than people in lower ranks, but maybe not. So we want to know, are mean salaries different? Are mean salaries different? And this is a really good question, and it's one we've been asking at my university because we have salary compression, right? We're hiring these young, hotshot economists, and they're awesome. And I don't spite them at all. They're fantastic, but they're getting really good salaries, and they're not that much below where I am. That's what we mean by salary compression. So this is a reasonable study and a reasonable question to ask. Are associates paid more than assistants, and are fulls paid more than associates? Because with salary compression, this may not be the case. It might not be that statistically significantly different. So we have here, this is interesting output here because it's actually telling us the null hypothesis and the alternate hypothesis. So you see the null hypothesis is usually there's no difference, right? Assistant professors equal to associate, assistant is equal to professor, associate is equal to professor. All right. So they're setting up their null hypotheses just a little bit different than I am. Remember, I've been setting them up where whatever's not in the alternate hypothesis is in the null hypothesis. And not everyone does that, but technically that would be correct, but this would be too. We're not going to make that distinction. I think the way I've taught you is maybe a little bit easier to get your brain around if this is new to you. All right, so our hypotheses are given here, and as I said, they're written slightly differently, but you see that they are being set up as one-tailed tests, right? One-tailed tests, and I can tell that because my alternate hypotheses are directional hypotheses. Let's focus in on the p-value. The p-value, well, again, remember, p-values are usually reported for two-tailed tests. This might have come from a statistical package where you can state what you want it to do, one-tailed or two-tailed. I don't know. But if it's two-tailed, we have to convert to one-tailed, which means, again, divide in half. But these are already really tiny numbers, right? 0.001. is what, 0.1%. So these are already really tiny, right? With a p of 0.001, less than 0.001. So I'm not going to worry about dividing these out. We can assume that either these are already converted to one-tails, or if we divide it in half, the number's still going to be teeny tiny. Let's look at our first hypothesis test. What can we conclude about assistant versus associate? What can we conclude about assistant versus associate? Well, we have a p less than 0.001. What can we conclude here? So think about what that means. it means that there's only a tiny chance of making an error, right? A tiny chance of making an error. And what error is that? That we would reject the null hypothesis saying, hey, there really is a difference when it's actually true, right? So our error that we could make is that we reject the null hypothesis when it's actually true, right? So that there's a statistically significant difference in means is what we can conclude here, right? The chance of making this error is teeny tiny, right? We can reject the null hypothesis because there's a teeny tiny chance that we get it wrong. Does everyone agree that we can say we are 99% confident, right? We are 99% confident. So this is a pretty strong result. So going back to our hypotheses, we are saying that there is a lot of statistical evidence to suggest that associate professors make more than assistant professors. Okay, well, let's look at the column called diff. We see that the difference in salaries is $13,100-ish, right? So what we're saying is that difference is big enough to be considered statistically significantly different. It is not due to chance in terms of our samples. Well, let's look at assistant versus full. All right, assistant versus full. That's the next thing down, the top hypothesis that I have, the middle one, but the top one that I have outlined. And then what about associate versus full? And that is the bottom hypothesis. So what can we conclude about those? Well, let's look at the p-values. Do you agree that the p-value is less than 0.001, which again means there's a very small, teeny tiny probability of making an error, that we reject the null hypothesis when it's actually true. So we can conclude that there's a statistically significant difference in mean salaries when we compare professors and associate professors and professors and assistant professors. But again, let's look at that diff column. We're seeing some pretty big differences. If we look at assistants versus professors, the middle column, we get $45,996 difference in salary. And for associates versus professors, we're looking at a difference of $32,895. So those are some pretty significant differences in salaries, and they are statistically significantly different. In other words, we reject the null hypothesis that their salaries, their mean salaries, are different, meaning we are 99% confident. All right, gang, so we understand how to read our output. We can do a t-test, kind of the long-handed way, I'll call it, looking at our t-critical versus our t-statistic, and we can do it looking at our p-values. We need to understand what assumptions we're making when we're testing for differences in means. If you do a statistical test and you use a package that's going to ask you, are the variances in the two samples equal or not? We have to pick an assumption. Are the variances in the two samples equal or not? Remember, variance is the squared standard deviation. So it's a measure of spread, right? It's a measure of spread or dispersion. So we're going to work under the assumption that our standard deviations, our variances, are equal. So if that comes up, the type of test that we're going to assume is going to assume that variances are equal. Now, gang, the good news is that there are other tests that you could conduct that work exactly the same way as what we just did. For example, we could test for differences in proportions. If you know how to do what we just did, testing for differences in proportions isn't really that different. You just have to look it up, but you'll understand it if you understand what we just did. So what do we mean by differences in proportions? Maybe we're looking at the proportion of male students who passed a test versus the proportion of females, right? The percentage of. Or we might be doing a paired test. So a paired test is interesting because I can look at person one before and after, let's say a medication, and say, oh, the difference is 5 for whatever I'm measuring. And then I do the same for person 2, before and after. Their difference is 7. And then person 3, before and after. The difference is 11. Do you see why we call this a paired test? Because we're looking at pairing person 1 before with person 1 after, and person 2 before with person 2 after, to calculate the difference person by person by person. So we're pairing the two observations together for each person, hence calling it a paired test. But as I said, if you understand what we did, you can read about these kinds of tests and you'll be able to teach yourself how to do them. You need to know how to calculate degrees of freedom, and then how to program your computer package, your statistical package, but reading the results is going to be very similar. So very quickly, gang, our hypothesis tests are part of our inferential statistics portion of the class. We have learned how to craft a hypothesis test, considering if we have a directional hypothesis, which is one-tailed, or not. We can calculate our degrees of freedom, and now we can conduct a hypothesis test for a specified level of confidence, right? Now, we haven't learned how to plug it into the computer yet, but that's not the hard part. We understand that we need to compare the T statistic, the hurdler, to the critical T, the hurdle, or we can look at p-values. But as I said, it's important that you understand both, that you can do both. Any quizzes might ask you questions assuming one version or the other version, especially if I give you data to have to interpret, data or output rather. So please, guys, let me know if you have any questions at all. And thank you for listening. I hope you have a fantastic day.